Thank you, Marcia, for introducing me. I would like to start because I have to tell quite a lot on this Smart 2013 benchmark in which TNO Diana participated. Here's a quick overview from what you will hear the coming hour. First, I want to talk about the Smart 2013 benchmark, what it is, where it is about, a little bit about the history. Then we're going to talk shortly about the first stage of this benchmark, which is about the material properties and models. Then we're going to talk about the finite element model that we have used for the benchmarking. The second stage is about the eigenvalue analysis and the calibration of the model. Then we are going to talk about response spectrum analysis and pushover analysis. These were not parts of the benchmark, but have been performed by us to provide additional information on the model. Then we're going to talk about the third stage, which is the actual nonlinear transient dynamic analysis, of which the numerical results are being compared with the experimental results. And I will end with some conclusions and recommendations we have learned from this benchmark. The Smart 2013 benchmark. The SMART benchmarks are about seismic design and best estimate methods assessment for reinforced concrete buildings subjected to torsion and nonlinear effects. The torsion is one of the essential parts that is being included in this benchmarks. The first SMART benchmark was in 2008, and the intention is to have a SMART benchmark every 5 years. We didn't participate in the 2008 version, but we participate in the 2013 version. As you can see, this benchmark is organized by Énergie de France, the International Atomic Energy Agency, the Paris-Saclay Institute, and CEA, also a French research organization. The entire SMART project ran from 2011 to November 2014. For more information, I refer to the SMART 2013 website. The SMART 2013 benchmark. What are we going to test? We're going to test 1 in 4 scaled part of a CPY type nuclear electrical building. The scaled model is 3 meters by 2.5 meters by 3 meters 60s. It will be loaded with synthetic ground motions, scaled versions of the Northridge main shock and the Northridge aftershock. Note that due to the scaling, that 30 seconds of the original signal is equal to 15 seconds on the scaled model, because the Eigenfrequencies are a factor 2 higher on the scaled model than on the real model. Here's an overview of the actual experimental setup. At the bottom here, in green, you see the shaking table, which is being using 8 hydraulic actuators, 2 in each horizontal direction and 4 in vertical direction. Then we have the reinforced concrete building, 3 floors. It's sort of a skew form to get the torsion nicely in. As you can see, there's additional loading on the floors in the form of steel blocks, and the entire mock-up is instrumented with 87 accelerometers, and they can sample up to 1000 Hertz. These accelerometers are being used to record the response on the experiments, and these will be used to check the numerical results from the participants and see whether it's good or bad agreement, and how we can further improve the numerical procedures to better match the experimental results. The benchmark contained 4 stages. First stage is the characterization of the nonlinear constitutive laws, which actually means the material models being used for the concrete and reinforcement steel. The second stage is the eigenvalue analysis and the calibration of the model. In this stage, the eigenvalues measured from the structure as well as some input and output on two low intensity loads were provided to all the users, so the models could be tuned with respect to damping and other properties before the third stage, the blind computation with the high intensity loads will be started. So stage 3 is for us the most interesting part, because we want to see how good the numerical finite element model matches the experimental results without knowing beforehand what the experimental results are. And there was a fourth stage which was talking about the seismic fragility estimation, which is a probabilistic kind of calculation in which we didn't participate because the model we choose to use was too large in sense of degrees of freedom to do many different calculations required for probabilistic analysis. So T and O Diana were only active in the first 3 stages of the SMART 2013 benchmark. What are we going to do during the benchmark? What is being tested and evaluated? There are 2 runs, run 6 and 7. These were the runs I was talking about, the low intensity runs that were provided, both in the input and the output for the calibration and testing. The other runs, run 9, which is still a design signal, and the runs 11 to 23, the Northridge signals, are being used for the blind testing. As you can see, there are 4 runs with the Northridge earthquake. The first 3 are scaled, and the run 19 is the actual Northridge earthquake, so unscaled one with a peak ground acceleration of 1.11 g in x direction and 1.03 g in y direction, and almost 0.5 g in vertical direction, followed by 2 aftershocks. First one also scaled, and the last one is the real aftershock. As is important to tell is that all these runs were performed sequentially on the experiment, and therefore that means that also in the numerical analysis we would like to perform all the runs sequentially and taking the damage and the results from previous runs into account during the next runs. For the SMART 2013 benchmark, there were 42 participants that were also active in the first 3 stages. There were a few parties that also were involved in the 4th stage. Of these 42 participants, they were coming from 18 countries spread over 4 continents. 56% of the participants came from design offices, and 52% of the participants were involved in the nuclear field. I would like to show now the experiment of the Northridge main shock, which you can see here in this film that has been recorded during the actual experimental testing. Now let's come to the first stage. We're going to talk here about the material properties. Most data was provided by the organization and was based on our experimental values for both the concrete and the reinforcement. The cylindrical samples were used from each cast of the concrete and were used to determine the compressive strength, the tensile strength, and the Young's modulus. Prismatic samples were used for fracture analysis and some further cyclic tests. For the reinforcement steel, there were done tension tests on 3 samples of each diameter of reinforcement bar, and that give information on the yielding and ultimate strengths of the bars, the maximum elongation, and the Young's modulus of the steel. In stage 1, there were 10 single element or small element tests involved, 5 on the concrete, 1 on the steel, and 4 on the reinforced concrete. For the steel, just simple 1 elements, solid hexagonal elements we use. For instance, here where you have a cyclic test, so first loaded to the right and then loaded to the left. For the reinforced concrete test, there were small slabs made of a few elements, and they were loaded with some reinforcement bars. For the concrete material model, we choose to use the total strain crack model in Diana with the Hordijk tension softening model and the Torenfeld compressive strengths. We have used mostly the values provided by the organization. That means the experimental values, not the design values. For some we have used the design values. There has been a higher crack energy used than normal and that resulted in some tension stiffening that we would like to see as well in the model. So these values are higher than expected for normal concrete. Further, the values are more or less as expected. For the steel material model, we choose to go for mesus plasticity with Menegotto Pinto, because this is a model that is specific for cyclic loading and nicely has a Bauschinger effect, so it is absorbing energy during the cyclic movements. Then I would like to talk about the modeling itself. In this test, the shaking table is included in the modeling. This has come from the 2008 benchmark, where it turned out that the shaking table itself had significantly effect on the experiments, and in 2008 the table was not taken into account, and for the 2013 benchmark they have decided to include the shaking table. There was a model for the shaking table provided by the organization, but there were some connectivity problems in this model, so we've decided to remesh the entire model. It's because it's a fairly simple structure with horizontal and vertical plates. So we have redesigned it, or remodeled it ourselves using 25,000 curved shell elements with drilling degrees of freedom, the T18SH and the Q24SH elements. Also on those parts where you see here these red triangular arrows, these are the locations where the actuators are. So you see here the 4 horizontal ones, and you see here the vertical actuators. These are the points where the load is being applied, and we have chosen to apply the load as prescribed displacements. We had both the accelerations and the displacement. We have chosen to use the displacements. Later it turned out that the acceleration and the displacement signals were not equal, because the acceleration signals were filtered while the displacement data was raw data. This gives some numerical some differences in the results between the participants, because some people has used the accelerations as input and other people like TNO Diana have used the displacement signals as input. Now we come to the actual model of the scaled 3-story building. It's completely built with solid elements, Where many other people went for shell and beam kind of structures, we've chosen to use solid elements to avoid problems at wall-floor connections, because when using shell elements and beam elements, you always have some overlap in properties and reinforcement contributions. We don't want to do that. We want to go to a full solid model. So we modeled it with almost 72,000 solid elements, bricks and wedge elements, just linear ones, no quadratic ones. That has been done to limit the total number of degrees of freedom, because with this model we already came up to 372,000 degrees of freedom, and with quadratic elements and the same element size, this would go probably over or close to 1 million, which is going to be to take too long time to run each analysis. We wanted to have enough elements over the thickness of the foundation and the walls and the floors, so at least 4 elements are being used for thickness of walls or floors. In total, we have 107,000 nodes in the entire model. The modeling of the reinforcements. We have chosen to model all the reinforcement bars. There are nearly 1,300 bars in this model. All bars are modeled individually, and these are modeled as embedded reinforcements, which means that you can model your steel bars independently of your mesh, and the software calculates the intersections with the bars, with the elements, and the stiffness of the reinforcement bars is added to the stiffness in the elements. With this approach, actual forces in the reinforcement bar can be taken into account. Shear forces cannot be taken into account. The stirrups have not been modeled in our model. We stick to these reinforcement bars as depicted here in this illustration. Further, as you have already seen in the illustration earlier and in the movie, that there were many blocks of steel representing the additional mass of the building. We have chosen to not add more degrees of freedom at this stage and use the distributed surface mass elements. Alternatively, we could have modeled it with solid elements. That would have then have the advantage that the center of gravity of the additional mass blocks is more appropriate, because with this distributed surface elements placed on the floors, the actual center of mass of each individual block is lower than when it would have been when it was modeled with complete solid blocks for the additional mass. Then we come to the second stage, which was mainly the eigenvalue analysis, which was being used to check and calibrate the models. The eigenvalue analysis is a free vibration eigenvalue analysis, which means that we have the stiffness and the mass involved. So we want to determine the eigenfrequencies and want to see the mode shapes. We also get information on modal masses, effective masses, participation factors, and we could calculate the Rayleigh damping parameters from the eigenvalue analysis. The first eigenmode that we found was the sway mode in x direction. You see that because of the geometry of the building that it is already skew bending and introducing the torsion, what is an essential part of the smart benchmark. You can also nicely see it on the top view, that you see that the main motion is an X, but you see there is some skew bending in Y direction based due to this geometry. The effective mass of the first sway mode is 50% of the mass of the concrete building. So it's not 50% of the mass of the shaking table included only the mass of the reinforced concrete building itself. So the mass of the shaking table is not included in this 55%. The second eigenmode we find is the sway mode in the y direction. Also here you see a little bit this skew bending introducing already some torsion effects in the x direction as well. As you can see, the effective mass is almost the same as the sway mode in the y direction. It's also what you expect for these kind of sway modes. It's 55%, 54% in, and the first one was 55%. So it's really very close. It's as expected for this building. The third mode is, as you can nicely see from the top view, is the torsional eigenfrequency. The effective mass is relatively low because on one side it is moving, say, in the plus y direction. The other side is moving in the minus y direction. Because it's not symmetric, you will see a non-zero value for the effective mass. It is when the model is more or less symmetric, this can go to almost zero, and the effective mass for torsional modes is not a very useful quantity to use. There are other numbers that you can get from the eigenvalue analysis with torsional modes that are making more sense than the effective mass. Now we're going to look at the eigenfrequencies. The first values that you see here are the ones that are provided by the SMART organization. These are for the first mode 6.28, 7.86 for the second mode, and 16.5 for the third mode. It is a little bit unclear whether these are the values from a numerical model that the SMART organization used, or that there are the values that are actually measured on the building. We have performed several eigenfrequencies. The first one is with the reinforced concrete structure only, so no table, no added mass. Then we see relative high frequencies. Then we performed the structure with the additional mass. Since the amount of additional mass is fairly high, you see the eigenfrequencies more than half with the added mass included. Then we come to the point where we also include the shaking table, and then we see that still that the shaking table is made of steel. It's quite a rigid structure, but you see it has indeed quite some effect, quite a huge effect still on the eigenfrequencies found. So it means that the shaking table is indeed not so rigid as might have been expected from the beginning. But as we see when we've run this eigenfrequency analysis, we're still quite higher in the frequencies than the provided values from by the organization. So we have been closer looking at the model. We made estimates how much the Young's modulus or the stiffness should more or less be, and it turned out that the stiffness should be significantly lower than that we are using in this test. So we updated our model by using a reduced Young's modulus, as also is given by the SEPFIP 2010 model code, and we used 85% of the measured Young's modulus instead of the full measured Young's modulus. According to the SEPFIP 2010 model code, this needs to be done for all linear elastic analysis, what an eigenfrequency analysis is, to account for initial plastic strains, which causing some irreversible deformations. And we see when we use the reduced Young's modulus, so 85% of the measured Young's modulus, that we come closer to the provided values, but we are still too high. But further reducing the Young's modulus seems not to make sense. We have checked the amount of mass. The only thing with the mass is what I already said, that the center of gravity of the additional mass is slightly lower in our model than in the experiment, but that is not influencing the amount of mass itself. So since we were also provided with two linear elastic seismic runs, or the low intensity runs, where we know the input and the output, so we performed some Fourier transforms to check where the eigenfrequencies of the model are, not based on the provided values, but based on the response from the experimental structure. And then we see for the low frequencies, you see that the input and the response are in line, because structure is just following the input. But you see that starting from around 3 Hz, that you get amplification of the response of the structure with respect to the input signal. And you see that here we see a first peak in x direction, which we expect that this should be the first eigenfrequency then of the experimental structure. And we see that this value is very close to the value we found from our finite element model. So we have doubts that whether the provided value of 6.28 was correct. So we tuned in the end on the Fourier transform of the response. We did that for the first mode. We could find it in x direction. For the second mode, we found a peak around 9.5, 9.4. So we assumed that this is indeed the second mode, which was a sway mode in y. The third mode, it was almost impossible to see any difference. It's also the torsion mode, so it is also difficult to see that in the response. But at least based on these values, so the reduced Young's modulus, the added mass, and the shaking table into account, compared with the experimental results provided, we think that we have tuned our model quite well, and we are going to use this setup for the linear elastic analysis. Of course, in the nonlinear runs, we will not use the reduced Young's modulus, but we will start with the measured Young's modulus, because there we will see the initial effects and the irreversible deformations. They will come in because the numerical model can handle it. So there is no need to reduce it in that stage. From this information, so we now know that our eigenfrequencies are around 6.6, around 9, and between 15 and 20. The organization also have provided damping values that they have measured on the experiment. So they found 2.6 for the first mode, 4.2% on the second mode, and 5.5% for the third mode. We have used this information to tune our Rayleigh damping. We cannot fit those 3 points on the Rayleigh curve, so we have to make some concessions. We also know from the input that there are frequencies in the range of 1 Hertz in the input signal. That's also that we don't want to damp out. So instead of using something like this, which also fits the Rayleigh curve, we want to make sure that we had low damping also in the low frequency range to not take out energy from the input signal. So we have chosen to come with a maximum of 5% damping in the range of 0.5 to 15 Hertz and maximum 10% damping up to 30 Hertz. So our first 3 eigenfrequencies are matching quite well with the provided damping. We have less damping for the second mode, but the first and the third mode seem to be almost spot on with our chosen Rayleigh damping parameters. So when using Rayleigh damping, you normally have to make some concessions because it's not a straight line, it is frequency dependent. So you need to tune and choose wisely with your with your damping values. But this was the part that we could do the calibration, and we started with this, and we were going to look now at the linear transient analysis. It's the equation of motion. We used Rayleigh damping, which we updated with the tangent stiffness. For the linear transient analysis, this is not making sense, but we used the same command file also for the nonlinear transient analysis that will come in stage 3. So we kept it in, but it will not change much. As already said, the loading is provided as time load diagrams. We used prescribed displacements to load the model. We're using the default Newmark time integration method, which is implicit. We use consistent mass and damping matrices. Elements were linear. We took a step size of 2,000ths of a second. In this way, we were able to get a maximum frequency of 20.5 Hertz. So we have the first 3 eigenfrequencies well covered. We would like to go to the largest step size possible because we have a quite large and detailed model. So we would like to go to the largest time step to come to acceptable calculation times. We know that we're going to use quite some time to perform all these analysis. So it is quite essential that we think well about the time steps being used. But we also don't want to take too large time steps that we miss the modes that we have seen. So the choice is that we come to this value, then we have triggered them, and it is acceptable in the sense of calculation that we had available during the benchmark. As you can see from the results of the run 6, which was artificial signal, a design signal, you can see that the experimental values, which are in red, and the numerical values, they match really well. It's almost too nice to see. You see in some high frequency signals in our numerical results, which are not seen in the experiment as clearly as from the numerical results. But we see that the overall behavior for low intensity load is very nice. We have for run 6, we show here the top floor X direction. It is measured on one of the corners of the top of the building. And the same we did for run 7. Here we checked the Y direction. Also here you can see that there is a little bit of high frequency signal visible in the numerical analysis, which you don't see from the experimental results. But the overall agreement for the low intensity runs is fine. So we have good agreements in the periods and the amplitudes. So the frequencies are okay, the eigenfrequencies are okay. It looks that the Rayleigh damping is okay, and when we look to the amplitude values. So we think that with the chosen values, we have tuned our model quite well, and we are ready to go to the third stage to do the nonlinear transient analysis. But before we're going to do that, we first want to perform some additional linear response spectrum analysis, because we have this model available, and response spectrum analysis is not taking so much time. In this for this analysis, we needed to input the load as base excitation loads. So we didn't use the shaking table here, if I'm correct. Then we applied the accelerations, which were also available from the organization, directly in 3 directions on the foundation of the reinforced concrete building. The damping is included in the load spectrum, so we don't have to bother about Rayleigh damping. We have the signals based on 5%. There is a SRSS rule used to do the modal superposition during the response spectrum analysis. And the response spectrum analysis provides us already some insight in the runs we are going to do in the nonlinear states. We already can get some information on the principal stresses, which will be an indication on where we can expect cracking during the nonlinear transient dynamic analysis. As you can see already for run 11, you see that this small wall on the left side will be heavily loaded because there's a lot of high principal stresses here. You also see it here on the column, on the corners, and on this side wall. When we go to the run 13, run 11 and run 13 are already scaled versions of the North Ridge earthquake, which are increased in intensity. So for run 13, you already can see that the areas are already growing with respect to run 11. And when we go further, run 70, you see already almost up to the second floor that we have principal stresses that are beyond the tensile strength of the concrete. And when we go to the actual North Ridge earthquake, you already see that almost the entire building is exceeding the tensile strength. So expect cracks in many places there. You need to keep in mind that the loading of run 19, so the North Ridge earthquake, in magnitude is already 4 times stronger than this model is designed for. So we are well beyond the design capacity of the building. So we are really curious whether, what the results will be. We've seen the movie, so we know that the experiments keep standing after run 19. But how much damage there is, and what the numerical models will do, that is of interest for this heavy loading. This loading is also much higher than has been applied in the 2008 benchmark, because these areas beyond the design values are proven to be very interesting for during these experiments, and therefore much attention have to be paid to these runs in the 2013 benchmark. After the linear response spectrum analysis, we also have decided to do a static Pushover analysis. It's a nonlinear analysis, but static, so no damping, no cyclic behavior. So the Menegotto-Pinto model, the cyclic behavior, the Bausching effect, is not doing anything in the Pushover analysis. Normally you use a Pushover analysis for sway modes of high-rise buildings. The loading is shaped according to the mode, to the Eigenmode. So the pushover load is a summation of a vector times the mass times the mode shape, and this is the loading component. So this is for an X loading. So we have nonlinear material in the elements, so we can use the total strain-based crack model. We are using, of course, the embedded reinforcements. Shaking table is also not included here, it's also not of interest. We are going to perform the pushover analysis on the first 3 eigenmodes, so the 2 sway modes and the torsional mode, just to get an indication on the damage that we can expect. As can be seen from the results of the pushover analysis, so the maximum displacement and the horizontal force applied. Again, also what you've seen from the response spectrum analysis, a lot of cracks are going to be expected in the little wall on the left side. There is some plasticity in the reinforcements expected at the end of the pushover. It looks from these 3 modes that the sway mode in X direction will be the most critical one. You can see that here because the amount of cracks for the pushover analysis with the sway mode in Y direction is much smaller, and it's also a little spot of plasticity in the reinforcements. Then the torsion modes, we again see some cracking near corners, near at the foundation of the the connection of the foundation and the walls. Also one spot of plasticity in the reinforcements. So these response spectral analysis and pushover analysis give us already a little bit of indication from where to expect plasticity, the cracking, which modes are going to be the critical ones, which looks that it will be definitely the sway mode and X direction, but probably in combination with the third torsional mode, it can be that these will reveal the critical points during the nonlinear transient dynamic analysis. Now, the equation of motion, our linear elastic stiffness is we replace with the internal forces. Again, Rayleigh damping with updated tangent stiffness is used, loading with time load diagrams, prescribed displacement. The Newmark time method is the same type of mass and damping matrices, linear elements, same step sizes. So we're curious what will happen. Run 9 was still a low intensity run, artificial. Also, we see here with the nonlinear model, it's still a low intensity load. We still good agreement between the experiment in red and the numerical results. We're really quite happy with those results. Now we go to the first Northwich earthquake. This is run 11. We see also for the entire, say 14 seconds of the experiment, we have always calculated a little bit further than the experiments because we did them sequentially and we wanted to make sure that after one run the model comes to more or less a standstill, so we always added some intermediate time between the runs to make sure that the model is at standstill before the next run is loaded. As you already can see, first cracks are going to appear. We have here the accumulated crack width over the elements. See it near the column and especially on this small wall and near the connection of the lower walls with the foundation. Run 13, that is further building up the intensity of the Northwich earthquake. What's interesting here is that the numerical model, the black, you see is nicely picking up the eigenfrequency of the building, which you can also see in the experiment. But even when we had nicely tuned the damping for this first mode, it was spot on with our Rayleigh curve and the measurement. It appears that our damping, our numerical system, seems to be more damped than the experimental model. This is not completely clear why that happened. It may be that there was in the experiment, there was on the top floor, there was some metal piping applied, which had also an eigenfrequency in this range that we have not modeled in the numerical model, that due to its own eigen vibration also amplified the displacements more in the experimental model than in the numerical model. Here in the middle we have plotted the results of the response spectrum analysis, and you can see that the actual crack pattern as seen in the nonlinear analysis is quite well matching the areas that are cracking based on the response spectrum analysis. In run 17, so we have now are approaching the full Northwich run, we were approaching convergence problems, and the convergence problems came from this little wall where this wall was completely cracked, and since we were using the embedded reinforcements, we only could take actual forces, and we were not able to take the shearing forces in the reinforcements bar. So at this stage we have adapted our model. We have replaced our embedded reinforcements with bond slip reinforcements. That means that the reinforcements are during evaluation are being replaced by actual beam elements or truss elements, but we choose for the beam elements because we want to be able to take into account some shear force with an interface in a solid element. So we have now an interface behavior. We used quite high values for the interface stiffness, representing a fully bonded reinforcement bar. The only difference is then, because we have now beam elements, we are able to take up some shear forces in the reinforcement. Due to the large calculation times, unfortunately it was not possible to rerun all the previous analysis, so we had to start, say, with a clean run, so no initial damage. And you see that after run 17, if we compare it again to the response spectrum analysis, we see similar areas where cracks are occurring than in the nonlinear transient analysis. So now the big case, that is the run 19, so the main Northridge earthquake. As you can see from the results, the model is almost everywhere cracked. That was also expected from the response spectral analysis. As said, we have done this run starting from scratch, so no history from previous runs could be taken into account. And we even had to go to linear elastic steel material. So we were already far beyond the yielding capacity, because we started with a von Mises model with hardening, but that was not sufficient. It also turned out that during the experiments, one of the main reinforcement bars here have been completely pulled out of the foundation. So also in the experiment there was severe damage. Numerically, this can lead to convergence problems or stopping of the analysis. So we wanted to continue to perform also the aftershock calculation. So after doing several runs, we managed to come to an end when we used linear bond slip reinforcements. But you can say that from a numerical point of view, you are beyond your capacity, and actually the building is destroyed. And then we have the result for the aftershocks. Also here we started from no damage history, and here you can see that our numerical results are not matching the experimental results anymore, and that is to be expected, because if we look now at, if we start the aftershock, say from a clean model, so no previous damage, then you get this kind of damage pattern, same as predicted by the response spectrum analysis. But as we could have seen from the experiment, after the main shock, the building was heavily damaged, so it was the results are not good if we cannot take the damage history not into account for these aftershocks. So it is essential for the aftershocks that you take the main shocks, the history into account to get a good response. Now we have just a standalone result which nicely matches the response spectrum, but it doesn't represent the experimental results anymore. Here's now a quick look at the pushover results, because this is what we expected from the pushover analysis with respect to capacity. The same have we done for all the other runs. We have plotted those, and you can see the run 19 is here, but as said, we had to adapt the model compared to the pushover analysis. So with the linear elastic reinforcements, we came much further. Also run 17 was adapted, but you see that the runs that were actually with the same model as the pushover analysis are close, but you see that the transient analysis run seemed to go a little bit further than the pushover analysis. This brings us to the conclusions. So one main conclusion is that using solid elements seems to be straightforward. You have to do no tricks on the wall and floor connections. You can nicely put all your reinforcement bars in. For this model, what we use 10 seconds, so one smaller earthquake took us 3 days calculation time. We used here a multi-processor machine with enough memory to keep the database in memory, as well as the result file, so that helps. It has also been seen that the response spectrum analysis and the pushover analysis can be useful as predictions for what may happen in the transient dynamic analysis, so both for linear and nonlinear. We have seen that the numerical model had good agreement for the small excitations, and it also good agreement for large excitations with, of course, a correct model. And as long as the loading history of the structure is considered during the analysis, because we've seen with the aftershock standalone that it is not matching the experiments, but that is being expected, so that is not so strange. Just due to a lack of time and the deadline from the benchmark that we're not able to do these sequentially again. It has also become clear that when the concrete fails and there is shear loading, that the shear stiffness of reinforcement bars must be considered. That can be done then with this bond slip reinforcement, for example, using beam elements. We've seen also that the Rayleigh damping in itself is good to use during this kind of nonlinear transient dynamic analysis. It's not optimal because it has a certain shape, and in your entire frequency range you are forced with, but in general we were quite happy overall with the performance of the Rayleigh damping. We have a few recommendations looking back on this experiment and the results, and that one is from, it is already a large model, so why not use also solid elements for the additional mass to get the center of mass of these additional masses also on the correct location. We also should have included the metal piping system on the 3rd floor, but we left out. We could think about modeling also the stirrup reinforcements, but that seems to, compare to this result, not so essential as those things. What we also think can be an improvement, and being less dependent on your Rayleigh damping, is also use a dissipative material model for the concrete. And here you can think about Merkava cracked concrete curves in the total strain model, or go to a modified Merkava model, or the new Merkava Fukuura model which will become available in the next Diana version, Diana 10. As we already have mentioned, it seemed to be wise for this kind of heavily loaded constructions, structures, to use bond slip reinforcement to be able to take some shear stiffness of the reinforcements into account. And other advantage may be that you can use dedicated bond slip interface models, in which probably we will also then be able that reinforcement that became unbonded during the experiment, that we could have seen it in the numerical model as well. With our linear elastic interface model, with this high interface values representing fully bonded, we have not been able to see it, because we were also not aware that this was going to happen, so that we heard after the benchmark. What also have become clear, especially during the workshop after the Smart 13 project, is that it can be of useful to do some intermediate eigenvalue analysis, because the eigenvalue analysis can be used as damage indicators, because you can see at a certain moment when there is considerable damage that your frequencies of your eigenvalues will start dropping. These prove to be even sometimes better damage indicators than, for instance, the inter-story drift that is commonly used for this kind of buildings as a damage indicator. It's also useful to do model integrity checks, because it can reveal that parts of the building may get completely loose, resulting in very low eigenfrequencies. So you can either adapt your model or make some modifications to continue for parts, say, where some concrete would have been chipped off during the experiments or so. And of course, an intermediate eigenvalue analysis can be used to update your Rayleigh damping, because as it's known for concrete, for cracked concrete close to its crack and yielding points, or the compressive strengths, that there is considerably more damping than for say an undamaged concrete, which is not fully loaded. So you can play probably a little bit more by making your Rayleigh damping more variable during this analysis. This ends this presentation on the SMART 2013 benchmark. I would thank everyone for their attention, and hope you learned something from this presentation.